Hello, here's a quick review over 11.3 geometric sequences and series, and what are our big takeaways and what do we really need to know? So as we learned in 1 and 2, we were looking at arithmetic sequences and series and looking that those have to do with our jumps that have to deal with addition or subtraction. And we know that when we are dealing with geometric sequences and series, that the only difference is that a sequence simply means a list of numbers. A series means we actually add up those numbers. So these are absolutely tied together and related. And the reason that we call these geometric is that the difference, the way we get from one number to the next, is through multiplication or division. And so what we call that is we call that an R value. It's a common ratio. We know that a ratio is simply two numbers. Ratios are a fraction. We can write any whole number as a ratio. We could write 3 as 3 over 1, and it would be a fraction. It would be in ratio. And so as we move through, or if you are on any sort of standardized tests or anything, if you see that you have a first term, which we typically call A1, often you will see that A sub 0 as your first term. Basically, it's labeling our first ones. When we have a sequence, we always start with A sub 1. So when we have that, it will address either a D value or an R value. If you see a D value, you immediately know that it's an arithmetic sequence. If you see an R value, you're going to know that it's going to be a geometric sequence. This R always goes with geometric. So there's two things we need to take away from sequences and series. First, we need to know the formula for a sequence. And second, we need to know the formula for a series. So how do we look and figure out our formula? Well, as we are looking at our sequences, as our numbers are going from one to the next, we can ask ourselves for the generic form of a sequence. So we are looking specifically at any term in a sequence. These would be separated by a comma. This is not when they are added together. For any term in a sequence, we always start at the first term. So we're going to write our generic expression in relationship to this very first term. And then we're going to ask ourselves, how many times do I have to jump to get to that space? So if we were looking at the third location, so A sub 3, we start at our beginning and we would need to jump twice to get there. So wherever we are headed, we jump one less. And that's where we get our n minus 1 for our how many jumps that we are going. Because these are multiplied, so say we were multiplying by 2 each time, remember that when we are multiplying, we are dealing with exponents. Because I have 1, 2, now I have 2 2s. I could rewrite that as 2 squared. If I had 3, it would be 2 cubed. And so we've gone from our arithmetic sequences where we used our n minus 1 and we multiplied it on the outside by so this is our number of jumps by our common difference. Now instead we are taking our common ratio and we are raising it to the exponent because we are dealing with multiplication for that. So our generic form is for any term. So I can find any location in that entire sequence. We always take our very first term and then we're going to jump a certain number of times. We're going to jump a certain number of ratios, and however many jumps we have is going to be that exponent. So our first term times our common ratio raised to the number of jumps that we have. So if we were looking, let's look at this one. Find the 8th term here. So we have our generic expression. We would know that in this case, we have our a sub 1 value is -8 if we were to write that out. So where we start our sequence would be at -8. We know that each time that we jump, we are multiplying by 3/2, and we're going down to some unknown value. So we want to go all the way down to the 8th term. So where we plug in 8, that means our n is 8. That also means that we are going to jump 7 times. We can see that we've got 8 minus 1 gives us 7. So I start at -8, and I'm going to multiply times 3/2 7 times. The easiest way to write that is 3/2 raised to the 7th. We do our exponents first, then we multiply times our first value, and we get -2187 over 16, and make sure that that is just fully simplified for it. So now that we can use our generic formula to find any term of a sequence, we can also use it to find the different places. Because if we know that our generic form is a sub n, we started our first term, we've got our ratio times n raised to the n minus 1. If we have any of our variables, we can solve for all the other variables, because you have enough tools in your tool belt now to be able to rearrange this equation and solve for any variable that is left. So when we have our first term and our common ratio, then we can rewrite our equation of our sequence, because our unknown n is the only unknown left in our sequence equation. If we have just one single term and a common ratio, what they've given us now is we've been given a term, which means we have the value on the left side, and we also have an n value. So we can plug in a value on the left side, an n value, and we have our common ratio. So now our a sub 1, our first term, is our unknown. And we simply use the tools in our tool belt to solve for our unknown. If we have two terms, we have two equations. And according to our tool belt, where we have a system of equations, if we have two unknowns, we need two equations, and we can solve that through substitution or through elimination, either way. And so we can set up both of our equations with our unknowns. We know the term, which means we've been given our left side. We've also been given our n value, but we don't have our first term and we don't have our ratio for both of them. So we end up with two equations where we have two unknowns. So through substitution, we're going to solve our smaller equation for a single value. It was easier to solve it for a sub 1 here. I should have a sub 1. And then we're going to substitute it as a sub 1 into our second equation, and we're going to now solve for our r value. In this case, our variable is on the bottom, and we know what our exponent is, and so we can simply use roots to solve that. If we had, let's look at this one, if we knew our ratio and we didn't know our n value, when our variable is up in the exponent, then we use logarithms. So this is why we've had to put all of those different tools in our tool belt so that we can solve for any part of these unknowns in our equations here. So then how do we need to use our sequence part to then tie into our series? And when it comes to geometric series, it's written exactly the same as our arithmetic series. So we have a sum of any portion of that sequence. If it starts at 1, it means we start at the beginning. It could start from 5 to 8. We can break up those sequences and add up whatever parts we want. This is our instruction guide. It's going to tell us where we start, where we end, and the formula or the expression that gets us each of those terms. So technically, we could write out all of the terms if we wanted. The shortcut for finding the summation of a geometric series is, and you're just going to have to memorize this one, is we start with our first term. We're going to multiply it times 1 minus our common ratio times our number of jumps. And the things that you're going to see different here is when we're dealing with our sequences, our number of jumps is 1 less than the term that we are looking for. When we're dealing with the summation for the full series, the number of jumps is the same as the number of terms. So those are going to be identical. And then we've got 1 minus our common ratio. So technically what you're going to get in most instances is you're going to get a negative value here in the numerator. And you're also going to get a negative value here in the denominator. And those two negative values are going to cancel each other out. Okay, so if we have this series, 1 plus 5 plus 25 plus 125, it could have been written as a sequence. If we rewrote it with commas without the addition, it would be considered a sequence. So we've taken our sequence, we've turned it into our series, and first, we want to add up the first 10 terms. Well, unfortunately, we don't know what the first 10 terms are. So to find the first 10 terms, we have to find the 10th term here. So to find the 10th term, we actually use our sequence because we are looking for the spot in the list. When we look for our spot in the list, we use our sequence equation, and that is for any term, we start at our first term and we multiply times our common ratio, and 1 less than our term for our jumps is our exponent. So we're going to plug in our first term is 1, our common ratio is times 5, so that's going to be 5. And to find the 10th term, we've got to jump there 9 times. Okay. Now, if we wanted to add it up, the first 10 terms, you could write them all out and then go ahead and add them up, or we can memorize our summation formula. So if I'm summing up 10 terms, that means my n here is my terms. So the sum of 10 terms, my first value we know is 1. We know we are jumping by 5, so I'm going to have 1 minus 5. And I've got 10 of those, raised to the 10, over 1 minus 5. At this point, we are simply plugging away using our calculator to come up with an answer. So the finality of sequences and series that you need to know, and I have a couple of examples on our slides here, is that the formula for a sequence is our first term times our common ratio raised to the 1 less number of jumps that we've got. And when we are summing it up, it's our first term times 1 minus our common ratio raised to the same number of terms that we are adding divided by 1 minus r. And as long as you have one of these values or two of these values in with two different situations, we can solve for any of our unknowns because your tools in your tool belt have enough to solve for that. So these are the two most important formulas for 11.3 and to know how to use them and what the different values mean.